Welcome back to ECE 320A. In this short video, what we want to just drive home is the point that the Laplace transform is a linear operation. It enjoys the two properties of homogeneity and superposition, which, when those are combined, give us linear properties for the Laplace transform. Again, you're in chapter 12 of the textbook, and we want to now learn a little bit more, or in this particular video, we want to talk about the linearity property of the Laplace transform. Homogeneity simply means that if we had a waveform, f of t, and if we scaled that waveform by a constant a, then Laplace transform, that constant a can be factored out of the Laplace transform in a sense, and the Laplace transform of a scaled waveform is just the scaled Laplace transform of the original waveform. Where in this particular discussion, a is a constant, that is i.e., so here I'm using the math abbreviation for that is, and I may use that throughout the rest of the course, so let me just make sure we're clear on that, i.e., that is a as a variable is not a function of time t or the original waveform f of t. As long as a is a constant, it's not a function of t, or it's not some scaled version of f of t, it's just a, then it factors out of the Laplace transform integral, which is integrating with respect to time. And now if we scale the original waveform in time, we scale the Laplace transform by that same amount. The second property that we need in order to have the Laplace transform being a linear, observing or being a linear operator is superposition, and that says that if we have two waveforms, f sub 1 of t and f sub 2 of t, then if we Laplace transform that sum, that's the same as summing the individual Laplace transforms, the Laplace transform of f sub 1 of t, which is capital F sub 1 of s, and adding that to the Laplace transform of f sub 2 of t, which is capital F sub 2 of s. Combining these two, homogeneity and superposition properties, allows us to have a Laplace transform that it obeys or has linearity properties. And because of that, now whenever we want to, we can apply the Laplace transform to each individual circuit element or variable and do that separately and then put all of the pieces together. And that's convenient in circuit analysis because that allows us to take these differential equations, and we will subsequently learn how we can actually move the circuit immediately into the frequency domain, or translate that time domain circuit into a frequency domain equivalent circuit, solve in the frequency domain that circuit, and then back out the results back into the time domain. But initially, let's just worry about taking a differential equation, which is now in the time domain, and running across the classroom and taking that into the frequency domain by means of the Laplace transform. and converting this differential equation or set of differential equations into algebraic equations by means of the Laplace transform, and that will actually allow us to be able to solve these problems probably in your mind a little more easily or smoothly.